A traditional architectural blueprint offers precise geometry, but it is completely blind to environmental stresses. When physical mass meets wind, solar radiation, and thermal transfer, static lines cannot predict structural behavior. To solve this, engineers use Building Performance Simulation, or BPS. This is the application of physics-based computer models to forecast exactly how a proposed design will react to real-world conditions. Instead of waiting for physical construction to discover an architectural failure, BPS allows us to run highly accurate tests on energy consumption, natural light quality, and wind flow entirely during the design phase. We divide these environmental forces into distinct categories called simulation domains. Each domain isolates a specific physical phenomenon, like thermal heat transfer, natural daylight penetration, or the fluid movement of air. Navigating modern architecture and government compliance requires memorizing a strict mapping matrix. You must know exactly which simulation domain you are testing, the specific mathematical metric required to measure it, and the exact software engine certified to run the calculation. Without explicitly linking these domains to precise metrics, achieving compliance with rigorous regulatory standards like the Energy Conservation Building Code, or ECBC, is mathematically impossible. We begin with the most heavily regulated domain, energy modeling. This simulation predicts the annual electrical consumption required to power the building's HVAC systems, its overhead lighting, and internal equipment. Proving its efficiency requires a strict comparative analysis. Regulators do not look at a design's energy use in isolation. They mandate testing the proposed building against a specific control model. That control model is the baseline building. It precisely matches your proposed building's geometry, built to bare minimum code requirements. The simulation pits this baseline model directly against your proposed design, running highly optimized systems. This head-to-head test outputs a single metric, the Energy Performance Index, or EPI. In a vertical bar chart, the horizontal line is the baseline limit. Your proposed design's energy bar must drop significantly below this threshold to prove efficiency. The industry-standard computational engine responsible for calculating this EPI is EnergyPlus, which is frequently accessed through visual interfaces like Design Builder. EnergyPlus is chosen for its immense computational depth, executing simultaneous simulations of energy, water, and ventilation flows throughout every zone of a structure. Achieving a compliant EPI through this engine provides hard empirical proof that your architectural design actively conserves resources when compared to the absolute worst-case legal scenario. The second major simulation domain focuses strictly on visual environment, daylight simulation. Here, architects must solve a persistent physical tension. You need to maximize the deep penetration of natural light to reduce electrical loads, but you must simultaneously mitigate the severe heat glare that large glass surfaces invite. To quantify natural light penetration, we use a metric called spatial daylight autonomy, abbreviated as SDA. SDA operates on a strict mathematical definition. It measures the percentage of total floor area that receives a specific, sufficient lux level of daylight for a set number of hours per year. However, high SDA scores often bring high thermal loads. The required countermetric is annual sunlight exposure, or ASE. ASE flags interior zones risking excessive heat. Areas closest to the perimeter mathematically breach the thermal threshold due to overexposure. Running high-fidelity visual comfort analysis to track both SDA and ASE requires advanced ray tracing engines, primarily Climate Studio and Radiance. Successful daylighting is not a matter of simply drawing larger windows. It is the direct result of solving the mathematical equation that balances autonomy against exposure risk. Next, we zoom out, shifting the scale of evaluation from a single interior floor plate to a high-density multi-tower urban cluster. This introduces the third technical domain, computational fluid dynamics, or CFD. CFD calculates the complex simulation of airflow vectors and heat distribution as they interact with irregular physical geometries. In urban planning, CFD is crucial for identifying severe microclimates. For example, it detects the detrimental wind tunnel effect created by tight corridors between high-rise developments, like those seen in Norella. Internally, CFD also serves a crucial life safety function. Engineers use it to track natural ventilation effectiveness, ensuring enclosed spaces like basement parking garages do not accumulate stagnant, toxic air. Operating concurrently with fluid dynamics is shadow analysis, which maps spatial blockage over time. Studying a proposed building's shadow trajectory is necessary to measure the exact negative impact your massing will have on the natural light access of neighboring plots. Furthermore, strict shadow mapping is required to prove that your own roof structure will not block sunlight from hitting your planned solar panel arrays. Urban structures do not exist in a vacuum. The data extracted from CFD and shadow mapping proves empirically that a building's localized physics will disrupt the surrounding environment. The BPS software market is dense. Extracting accurate metrics requires selecting the correct analytical tool for your specific phase of development. The first software category focuses on early-stage BIM-integrated quick energy analysis used during initial building massing. Viewing this software matrix, the first column highlights Autodesk Insight and Revit as the industry standards for rapid, low-resolution iteration before the geometry is locked. The second category is comprehensive environmental analysis. The center column features IESV for simultaneous energy, light, and evacuation tests. The final column is cloud-based optimization, where Cove.tool maps construction costs against energy performance for peak financial efficiency. A professional's leverage in this industry lies in knowing exactly which engine to deploy, dictating whether the project needs a rapid directional estimate or a mathematically rigorous legal compliance metric. All of these isolated tests ultimately point back to a single, unified architectural geometry. The matrix is rigid. The energy domain relies on the EnergyPlus engine to output the EPI metric. The light domain requires Radiance engines to calculate the SDA metric, and the fluid domain utilizes CFD to map and resolve urban wind constraints. These independent physics engines operate concurrently. They analyze the exact same spatial data, but process it through completely different mathematical perspectives. Modern regulatory frameworks, including DDA guidelines and ECBC mandates, explicitly require this level of multi-domain empirical proof before a permit is issued. Designing an aesthetically pleasing spatial volume is no longer sufficient. Architects must mathematically prove that the volume functions efficiently under stress. Building performance simulation acts as the ultimate translation layer, taking static architectural ideas and turning them into dynamic, predictable, and legally compliant physical realities.